Um, Hello guys, today we're going to study a new kind of integrals, which is section 7.2. We're going to study the trigonometric integrals. So our objectives are going to be to evaluate trigonometric integrals, which of the forms of the following forms. So the first kind is the integral of sine x to the power n times cosine x to the power m with respect to x. And the second one is integral of the tangent raised to the power m times the secant raised to the power n. And the third one, which is typically like the second type, cotangent x to the power m times cosecant x to the power n. And finally, the product of sine ax and cosine bx dx. And we're going to attack this kind of integrals using two things. The first thing is suitable substitution and or trigonometric identities. Okay, so this is our objectives. Let's see some examples. We know how to integrate sine and cosine. Yes, integration of sine is negative cosine plus c, since this is the antiderivative of the sine. If you differentiate this, you will get the sine x. Okay, and also we know the integration of cosine x dx. Okay, which is sine x plus c. Again, if you differentiate the sine, you will get cosine. So this is the antiderivative of the cosine. And also, in the previous sections or previous chapter, we know how to integrate sine square x dx and cosine square x. And actually, we do that using the double angle formula. We know that sine square x equals half times 1 minus cosine 2x. So if I call this is I, so I is going to be half, which can be written before the integral sign, times 1 minus cosine 2x dx, and then you integrate simply. It will be half times x minus the integration of the sine of the cosine is sine 2x, and then you have to divide by 2 because of the chain rule. Okay, and also you can do the same for cosine square x with respect to x. I will leave it to you. You know that you will use the double angle formula, which is half times 1 plus cosine 2x. Okay, so do it yourself. Okay, so we know many some information about the trig integrals, but today we are interested in this kind of integrals, which is a little bit more complicated. So sine x to the power n times cosine x to the power n with respect to x. So let's begin with this one. Okay. So let's see some little bit hard examples. So we're going to begin with this one. So example, And so we want to calculate the integral, or to evaluate the integral of cosine cube x dx. Okay, so let's see our first trial. So maybe you can think that you could use this substitution that u equal cosine x, but when you get the differential of u, you will get negative sine x dx. Okay, so unfortunately, to use this substitution, you have to have an extra sign factor here, which is not here. So I think it will make it more complicated. So we cannot use this substitution, but maybe we can try in another way. So this is our integral, which is cosine cube x dx. Okay, so maybe you could think like that. It's okay if I wrote it as cosine square x times cosine x dx. Okay, so now we can look to this as d of sine x. So now somehow we can say that, okay, if we can convert everything here, if we can rewrite everything here in terms of sine x, so in this case we can use this substitution, which is u equal sine x, and u will be cosine x dx. So let's try it. Okay, so now if we consider this substitution, so our integral is going to be cosine square. I can rewrite it in terms of sine x using this formula, this famous one, cosine square x plus sine square x equal 1. So you can see that cosine square x equal 1 minus sine square x. So I can rewrite our cosine square x as 1 minus sine square times cosine x dx, and then we will use our substitution. So now instead of sine x, I will replace each sine x by u and cosine x dx by du. Okay, so now what is going to be 1 minus u squared times du, which is easy to integrate. So it's like 1. So the integration now is going to be 1 minus u minus u cube over 3 plus c, and then you have to rewrite everything in terms of x. Okay, so we're going to replace u again by sine x. So you will have sine x minus sine cube x over 3 plus c, and this is the required answer. Okay, and this is our answer. Okay, so now let's check it again. Why this works? Actually, when you just separate a factor, a cosine factor here, and the rest of this function can be written in terms of sine x, so we could use this substitution and solve it easily. So the point here is that you want to separate this cosine factor, and then you have to look to this power. Why is this power? Because if this power is odd, we cannot use this formula. We will not be able to write the rest as a function in sine x, and then we will not be able to use this substitution. Okay, so let's see another example. So the point here, before we go to this example, the point here again that when you separate this cosine, okay, the power here is even, so you need this power to be odd. So let's see another example. Okay, example 2. Let's make it a little bit more complicated. So you have the integral of sine to the power 5 times cosine square x dx. Okay, so let's think how can we do that. So maybe you could think that in this way, that maybe you will replace, you said I will replace cosine x to be 1 minus sine square x. Okay, let's see our integral. So our integral is going to be, okay, sine to the power 5 minus sine to the power 7, yes. And to use this substitution, which is u equal sine x, you need an extra factor here, which is cosine, because u is going to be cosine x dx, and this extra factor is not here. So I think this is going to be more complicated in this way. So it doesn't work in this way. So let's think in a different way. So let's think in this way. So trial 2. So maybe you think that you will rewrite your integral in this way: sine to the power 5x times cosine x, and then you're going to separate or to save another cosine x factor in this way, such that this is the differentiation of sine x, the total differentiation of sine x. But again, if you think in this way, so you need to say that u is going to be sine x. Okay? So you have to write everything here in terms of sine x. So this part is okay, but what about the cosine? So the cosine here will make a problem, because the power of this cosine is odd, which when it's odd, we cannot use this relation anymore. So we have to find another way. So let's see another trick, which will be also the same as in the first example. Look here in the first example, the power of the cosine which we separated was odd. Okay, so when you separate it again, you get an even power, so you can use this nice formula. But here, when you try to do that with the cosine again, the power was even. So when you separate it, you will start with cosine raised to an odd power. Okay, but actually we can try this trick here with the sine, not with the cosine. Okay, let's see it. So our third trial. So again, our integral is the integral of sine to the power 5 times cosine square. Okay, so let's try it with this sine. So we're going to save a sine factor here, and then the rest is going to be sine to the power 4 times cosine square x. Okay, so this part is the same as the total differentiation of somehow cosine x. It will be negative cosine x. Okay, so if you want to use this formula, which is u equal cosine x, so you have to write everything here in terms of sine. In terms of cosine, to use this substitution. So this part is okay. So this part is okay, and this part actually, since the power here is even, so you can use this nice formula, which is sine square x plus cosine square x equal 1. So actually, this can be written as sine square x all square, which is the same as 1 minus cosine square x all to the power 2. So if we're going to use this substitution, so our integral equals the integration of sine to the power 4 is going to be 1 minus cosine square all square. So it's 1 minus cosine square, which is u square all squared, and then times cosine square, which is u square, and then du here is negative sine x dx, and actually we have this factor here, which is the sine factor, so this is going to be negative, I will write it outside, as you know, times du. So now it's easy to integrate this function. So first we're going to expand this, so you will have 1 minus 2u square plus u to the power 4, and then times u squared u. And then you're going to distribute this u squared here. So we'll have negative 1 u squared, because you will multiply u squared here. So you will have u squared minus 2u to the power 4 plus u to the power 6 du. And then you integrate. So you will have negative u cubed over 3. And then you'll have plus, because this negative will multiply here, 2u to the power 5 over 5, plus or minus, because of this negative again, u to the power 7 over 7 plus constant. And then you have to replace each u by cosine x, because our integral in terms of x, so we have to get a function in x. So you will have negative cosine cube over 3 plus 2 cosine to the power 5 over 5 minus cosine to the power 7 over 7 plus c. And this is our integral. This is our required answer. Okay, so let's conclude what we have done here. So our conclusion for this case, if you have sine to the power m times cosine to the power n, so simply if one of them is odd, so let's consider first that the power of the sine is odd, so you're going to save one factor of the sine, and then you have to write everything in terms of cosine and use this substitution, which is cosine x. Okay, and you can write everything in terms, of course, you have to consider this famous relation. Okay, because this is the relation that will allow you to write everything in terms of cosine, and then simply you will solve with this substitution. The second case, if n is odd, which is the power of the cosine, so again, you will save one cosine factor, and you're going to use this substitution, which is u equal sine x, and you have to write the rest of this integrand as a function in sine x using this relation. Okay, and then you can solve easily. Okay, so this is the first part. So actually, so we know how to solve this, or we know how to attack this kind of integrals if the power of the sine and the cosine was odd. One of them is odd. Okay, so we know how to deal with that. But now, what about the other case? If m and n are even. So let's see an example. So let's go back for the easiest one, which is the integrand of sine square x dx, or cosine square x dx. So we say that, okay, here you can use the double angle formula, which says that sine square x equals half times 1 minus cosine 2x, and then you integrate easily. So it's going to be half times x minus sine 2x over 2 plus c. So, okay, so this is easy. Okay, but what about, for example, cosine x squared, or sine x to the power, sine, so what about sine x to the power 4? So consider this integral. So what we can do here? Okay, maybe you could think in the same way. So here we use the double angle formula, so maybe we can apply it here. So we can look to this integral as sine square x all squared, and then now, okay, let's use the double angle formula. So when you see sine square, whatever the angle, sine square ax, you have to use the double angle formula most of the time. So here sine square x is going to be half square, because there is a square, and then you will have 1 minus cosine 2x all squared. So we can expand this, so you will have 1 over 4 times the integral of 1 minus 2 cosine 2x. So we can integrate 1 and 2 cosine 2x, but still we will have an extra term here, which is cosine squared. We reach to this step, so we'll have I equals 1 over 4 times 1 minus 2 cosine 2x plus cosine squared 2x dx. So here we have to use the double angle formula. So cosine squared 2x equals half times 1 plus cosine, and then you have to double this angle. So this is 2x, so it will be 4x. So I is going to be 1 over 4, the integral of 1 minus 2 cosine 2x plus half cosine 4x, and then you have to integrate with respect to x. Okay, so you'll have 1 over 4, and now you can integrate easily. So the 1 is going to be x, and then 2 cosine 2x, it will be sine 2x over 2, and then you'll have half x, okay, and then you'll have half, and then you have sine 4x over 4 plus c. Okay, so it's going to be, so we'll have 1 over 4, it's simplified, so x and half x is going to be 3 over 2 x minus, and then these two will be cancelled, so it's going to be minus sine 2x plus 1 over 8 sine 4x, all of this plus c. Okay, so let's see another example. So we know that when we see when we have the power of the sine and the cosine are even, so we can easily use the double angle formula as much as we can to integrate our integral. So let's see another example. So okay, we want to integrate sine squared x cosine squared x dx. Okay, so now I will solve it in two ways actually. So the first one is so let's call this is I. So the first one is to substitute by the double angle formula for each one. So we'll have half, and instead of sine squared x, you will have 1 minus cosine 2x, and then you will have another half, and then you will have 1 plus cosine 2x, and you want to integrate it with respect to x. So it will be 1 over 4, 1/4 of, and then this is difference squared. So it will be 1 minus cosine squared 2x dx. So again, 1 minus cosine squared, which is sine squared 2x dx, and again you have sine squared x, so you have to use the double angle formula. So our integral will be 1 over 4, and then you will have half times the integral of 1 minus cosine 4x dx. So it will be 1 over 8, and then you integrate the 1, it's going to be x, and then the cosine will be sine 4x over 4 plus c. So this is the first method. Let's see another method which maybe make it much easier, or as you like. So again, you will have this sine squared cosine squared. I can rewrite as sine x times cosine x whole squared dx, and we can use again the double angle formula for the sine. So we know that sine 2x equals 2 sine x cosine x. So now our integral can be written as, since this is squared, so okay, let's do it step by step. So we'll have half sine 2x all squared dx. So it's 1 over 4, and then you will have sine squared 2x dx, and then you have the same. So now we get the same step. We got the same step, and then you continue. Okay, done. So let's conclude this case here. So we know that if the power of the sine and the cosine is even, so simply you have to use the double angle formula as much as you can to simplify your integrand. Okay, so let's conclude in this case, if m and n are even numbers, so we start with this one, which is sine to the power m times cosine to the power n with respect to x. So if m and n are even, so then you have to use the double angle formula, which is cosine square x equals half times 1 plus cosine 2x, and sine square x equals half times 1 minus cosine 2x. Okay, so this is our conclusion here. So now we done with this kind of. Okay, let's move to the second type, which is we want to integrate tan x to the power m times the secant to the power n. Okay, we're going to use the same a similar argument to evaluate these kind of integrals. So, but first you have to recall this important information, which is the differentiation of the tangent x is the secant square, and the differentiation of the secant x equals secant x times the tangent x of x. Okay, and also a similar relation here, which can be used from the first one, which is 1 plus tan square x equals the secant square. Okay, so using these three information, we will be able to discuss this kind of integral as before. So let's do it with an example. Okay, so consider this integral, which is tan to the power x, so the tangent to the power x to the power 6, times the secant to the power 4. Okay, so let's see our first trial. Okay, maybe you think in this way. Maybe you say, okay, let's separate this factor, say x tan x factor. Okay, so let's separate it, and we will see how can we proceed. So if we separate sec x times tan x, so you will have our integral is going to be tan x to the power 5 times sec cube, and then our factor, our saved factor here, which is secant x times tangent x with respect to x. Okay, so now this is the same as the differentiation or the differential of the secant. So if you want to use this substitution, you have to convert everything here. You have to rewrite this, the rest of the integrand as a function in. So this has to be written as a function in terms of the secant. So this part is okay because it's secant cube. But what about tan to the power 5? Okay, if you wish to use this one, so you have to have an even power of the tan. So the tan square here is secant square minus 1. So since this power is odd, so we stuck here and we cannot use this relation. Okay, so if we separate say x tan x, we cannot proceed. So this is our first trial, and it doesn't give us the solution. Okay, so let's see another trial. So second trial. Okay, let's separate secant square factor. Okay, let's separate a factor of the secant square. Okay, so our integral is going to be, in this way, is going to be the integration of tan to the power 6 times secant square times secant square x dx. Oh, okay, and this part is the same as the differential of tan x. So if I wish to use this substitution, I have to rewrite the rest of the integrand as a function in terms of tan x. Okay, so this part is okay, but what about the secant square? Okay, yeah. Now the power of the secant is even. Okay, so and since it's even, we can use this beautiful relation. So our integrand is going to be tan power x, so tan x to the power 6 times 1 plus tan square x times 6 square x dx. And now we can use this relation, which is u equal tan x. So our integral will be u to the power 6 times 1 plus u square times du. This is now our du. And now our integral is easy to integrate. So you have u to the power 6 plus u to the power 8 with respect to u. So we will have u to the power 7 over 7 plus u to the power 9 over 9 plus c, and then you have to rewrite everything in terms of x. So you have to replace u by its value, which is tan x. So you will have tan to the power 7 over 7 plus tan to the power 9 over 9 plus c, and we have done. So again, let's see why this is work. Why when we separate secant square factor, we could proceed. Okay, look, when you separate this secant square factor, you're going to use u equal tan x, this substitution. You're going to use this substitution, which is u equal tan x. Okay, so you have to rewrite everything in the integrand here, in the rest of the integrand, this remaining part. You have to write it in terms of tan x. So to do that, the rest of the secant should be with an even power. Okay, so this even power, yeah, but I already take 6 squared here. So to be able to solve in this way by separating, by using this substitution, you have to have the secant with an even power. So let's conclude this case. Okay, if you have this integral, which is tan to the power m times sec to the power n with respect to x, and the same is going to be for the cotan to the power m times the cosec to the power n. Okay, so again here you're going to use 1 plus tan x equals secant square x, and if our case here is that if the power of the secant is even, so if it's even, easily you are going to save a secant square, okay, and even, which is not 0, okay, because 0 is even also. So you're going to save a secant square factor, okay, as we did. As we did here, we saved a secant square factor, and then we rewrite the rest, or the remaining of the integrand as a function in tan of x. So okay, so if it's even, so we're going to use this substitution as we did here, tan x u equals tan x, and then you proceed, and it's going to work. Okay, so this is a first case. Okay, let's see another example. Okay. Example. Okay. So consider this integral, which is tan to the power 5 times secant to the power 7. Okay. Okay. So maybe one of you say, okay, let's try to do the same as we did here. Yeah, we know that here we said that the power of the secant should be even, but why does it work if it's odd? So let's see that. So okay, let's have this factor, which is secant squared x dx as before, and then here you will have tan to the power 5 times sec to the power 5. Okay. Okay, so this is the same as the differentiation of total differentiation of 10x. So now, if you wish to use this substitution, you have to write everything here in terms of 10x. So this is fine, but what about this? This is secant for raised to the power 5. So here, actually, we cannot use this relation because this power is odd. So we're stuck in this way, and we could not use this trick as we did in the last example. But let's see another thing. We know that the differentiation, as we saw here, the differentiation of the secant is secant times the tangent. Okay, so maybe we could separate this factor here now. So let's see. So maybe I will separate secant x times tan x factor. It's going to be 10 to the power 4 times sec to the power 6 times sec x with respect to x. And again, this is the total differentiation of sec. If you wish to use this substitution, you have to write everything here in terms of sec of the secant. So this is okay. But what about this? Now, this is the point. The power here is even. So this can be written as tan square all square. Okay? Then this is even, so tan square. You can write tan square as 6 square minus 1. Okay? And in this way you can proceed. Okay, let's continue. So this substitution all squared times secant to the power 6, which is u to the power 6, and then du. And now this is easy to integrate. So this is like, you expand it, you will have u to the power 4 minus 2u squared plus 1 times u to the power 6 du. So it's u to the power 10 minus 2u to the power 8 plus u to the power 6 with respect to u, which is easy to integrate. So you will have u to the power 11 over 11 minus 2 u to the power 9 over 9 plus u to the power 7 over 7 plus constant. And then you have to replace u by secant x. So you will have sec to the power 11 over 11 minus 2 over 9 sec to the power 9 plus sec to the power 7 over 7 plus c. And in this way we did it. So, okay, what is the main point here? The main point here is that we separate sec x times tan x, okay? And then we could proceed because the power of the tan was even in the remaining part. So we separate just one tan here. So it's going to work if the power of the tan is odd. So this argument is going to work if the power of the tan is odd. Okay, so we can conclude the second case here now. Okay, so again with the same integral, so tan to the power m times secant to the power m. Okay, so if and the same for the cotan and the cosecant. Okay, so if the power of the tan is odd, so actually you can use directly this substitution, which is u equal secant x. We said that to apply this method in the case of m is odd, you have to have you have to separate sec tan, and then you're going to use this substitution. But actually you can do that only if n is not equal to 0. If n is 0, the secant will disappear, so you will not be able to separate this factor, which is sec times tan. So let's see what will happen if n is 0 in this case. Okay, so if n is 0 in this case, so this integral is going to be just the integral of tan to the power m x dx, and where m is odd. So let's see some examples. Now we cannot separate for sure secant x times tan x, so we have to find another way, or if we can. So let's consider the first example here, that the integration of tan x dx. So there is no secant, so we cannot apply the last case. But fortunately this is easy, because we can rewrite tan as sine x over cosine x, which can be integrated as since the differentiation of the denominator is negative sign, so simply you can multiply by negative and negative, so it will be negative ln the absolute value of cosine x plus c, which is the same as ln sec x plus c. So this was the first example. Another example where n is 0, where we don't have the secant, so is the integration of tan cube x dx, and this actually it's not hard. So you can look to this as tan x times tan square x dx, and then you will replace tan square by its value in terms of the secant. So we will have tan x times secant square minus 1 with respect to x. So we will have the first integral will be tan x times secant square x dx minus the second one, which is the integration of tan x. And actually this is not hard. So the first part easily will be if you use this substitution, which is u equals tan x, so I is going to be tan x squared over 2. So this is the first integral, and the second one is going to be, as we have seen, ln the absolute value of sec x plus constant, and in this way it's done. Okay, so these two examples was a missing case in the last part, in the last case. Okay, now we will go for the last sub case, which is a little bit complicated. That again you have this integral tan to the power m times the secant to power n. Okay, but in this case m is even and n is odd. I want to see how can we deal with this case. Okay, so let's see some examples. So the first one is the integral of sec x dx, which is not hard, but it's tricky. Okay, so now the power of the secant is 1. Okay, so it's odd, and the power of the tan is 0, so which is even. So we are in this case. Okay, and this can be done easily. Actually, let's call this is I. So I is going to be the integral of sec x. So actually, you can multiply up and down by sec plus tan over sec plus tan with respect to x, and then you will have sec x plus tan x in the denominator, and up in the numerator you will have sec square x plus sec x tan x with respect to x. And now you can see that the differentiation of the secant x is sec x times tan x, and the differentiation of the tangent is secant squared. So now the numerator is a differentiation of the denominator, so directly the integration is going to be then the absolute value of the denominator plus constant. So now we did it. Let's see another example also regarding this case, which is now it's somehow complicated, which is this integral I equals the integration of secant cube x dx. Okay, our integral is the integration of sec cube x dx. Okay, we can rewrite it as again sec x times sec square x. And here you cannot think in the same way that maybe you say, okay, you say that I will do it as before, that this will be maybe I can choose you. I can choose u to be tan x. But in this way, you have to write everything in terms of tan. And the rest of the remaining part of the integrand have to be written in terms of tan, and this is not easy because you will have like a square root because the power here is odd, so this doesn't work here. Okay, but actually we still can do another thing here. You know, in the last section you studied the integration by parts, so maybe we can do the same here. So here we choose u to be a function which is easy to integrate, and we choose dv to be a function which is easy to integrate. Okay, so the differentiation here will be sec x times tan x dx, and v equals the integration of sec squared, which is tan x. So our integral equals uv, which is sec x tan x, minus the integral of v du, which is going to be sec x times tan square x dx. Okay, we did not finish. We don't know how to integrate this integral, but maybe we can substitute by the value of tan square, which is secant square minus 1, and in this way our integral will be I equals again sec x tan x minus the first thing you will multiply this secant by secant square, so you will have secant cube x dx, and then you will have sec x times negative 1, but again you have another negative here, so it will be plus sec x dx. Okay, and now we have some good news that again this is I. Yes, so if we take it to the other side, you will have 2I equals sec x tan x, and then plus this integral, which is easy, that we just have done. We just did it, so it lends the absolute value of sec x plus tan x. Okay. We done with this example. So, and I will leave another example as an exercise for you that try to evaluate this integral, which is the integral of tan square x times secant x dx. Okay. So in conclusion, this integral in this case, so the integral of tan x to the power n times secant x to the power n, where m is even and n is odd, can be attacked in this way. Maybe you try to express it completely in terms of the secant, and then use the integration by parts. Okay, as we had done, as we see in the last example here, we have it already in terms of the secant, so and then we apply the integration by parts, and also the one before this example, which was here, and also you have to do the same thing here. So if you want to solve this one, so the first, if I call this is I, so the first thing you have to write this in terms of the secant. So how can you do that? So I'll give you a hint. You can do that by replacing tan squared by secant squared minus 1. So it would be secant squared minus 1 times secant x dx. So you will have the first one is the integration of secant cube, which we had done. So anyway, I solved it, minus the integration of the secant x that we also did it. Okay, so you can just copy the answers. Okay, and this way we're done with this case. Okay, here let's summarize what we did for this integral, which is tan x to the power m times secant x to the power n with respect to x. Okay, we have three main cases. The first case was if n, which is the power of the secant, is even. So if n is even, so you have to use this substitution, which is y equals tan x. But also you have to know that n cannot be 0, because actually when we attack this kind of this integration in this case, so you have to separate secant square. So if n, which is the power of secant, is 0, so you cannot separate it, so you cannot use this method here. So the second case is that if m, which is the power of the tangent, is odd. So if it's odd, so you have to use this substitution. So you have to use this substitution, which is u equals sec x. Okay, and also here n should not be 0, because actually in this case you're going to separate sec x tan x. So if n is equal to 0, which is the power of the secant, so you cannot separate sec x tan x, so you cannot use this method. And actually in the case of n equals 0 here, we saw some examples. Okay, we saw some examples like the integration of tan x and the integration of tan cube x dx. If n is odd and m is even, and in this case you have to write the integrand completely in terms of the secant, and then you have to use the integration by parts. Okay, as we saw in the last example. Now we're going to move to the last kind in this lecture, which is sine mx cosine nx dx, or sine mx times sine nx with respect to x, or cosine mx times cosine nx dx. Okay, so all the time we're going to use these relations: sine A cosine B equals half times sine A minus B plus sine A plus B. Okay, and the second one, sine A sine B equals half times cosine A minus B minus cosine A plus B. And the last one is cosine A times cosine B is half times cosine A minus B plus cosine A plus B. Okay, so using these three formulas, we're going to solve this kind of integrals. So let's see an example. Okay, so we have sine 4x times cosine 5x dx. Okay, so we're going to use the first formula here. So this, we call it I, so I equals the integral, and we can write this half outside, and then you'll have, so this is sine cosine, so this is like A and this is like B. Okay, so we'll have sine A minus B, which is 4x minus 5x, then plus sine a plus b, which is 4x plus 5x, all this with respect to x. So you'll have half, then the integration of sine negative x plus sine 9x dx. And we know that the sine function is an odd function, so it will be half integration negative sine x plus sine 9x with respect to x. And this integral is very easy. So I equals half times the integration of negative sine is cosine, because if you differentiate cosine you will get negative sine, and the differentiation of sine 9x is negative sine 9x, and then you have to divide by the differentiation of the angle because of the chain rule, and then you add a constant, and it's done. Okay, thank you.